Okay, so matrix operations or matrices and their operations. I'm calling determinant an operation. It's really not considered an operation, but you find the determinant of a matrix. So we're going to start with that. The determinant of a matrix. It's kind of like a property of that matrix. It only exists on square matrices. They have to be square matrix, which means it's got the same number of rows and columns, like 3 by 3, 2 by 2, M by M, whatever. They got to have the same number of rows, same number of columns to be able to find the determinant of a matrix. They're not the square matrix. You just can't find the determinant of them. There's no way. Okay. There's ways to do this by hand, and the calculator obviously can help us do that. But there are times when doing it by hand is quicker than the calculator, honestly. And that time that it's quicker is with a 2 by 2 matrix. So a 2 by 2 matrix it would be something like A, B, C, and D. 4 elements in there, 2 rows, 2 columns. It's going to have numbers in there. If I ask you to find the determinant of A, B, C, D, the notation that can be used for that, when you look at this on a ACT test or our test or whatever, they're going to use what looks like absolute value marks instead of the square brackets. It's just straight up and down. There's 2 different ways that they'll ask you to find the determinant. They'll use the abbreviation DET and then write the matrix, or if they've got a list of matrices, matrix A is this, they might write DET of A in parentheses there. Or they might do this with the straight up and down bars. So it's like absolute value marks instead of brackets on that. So it's a real subtle change in the notation there, but it means do that. And the way that the determinant of a 2 by 2 works, and I never do these with the calculator because it takes me too long to type them in because it's too easy to do. You just multiply diagonals. A times D minus B times C. And get that number. And that's the determinant of a 2 by 2 matrix. Really, really simple thing. So example A, let's do the determinant of 3, -2, 7, 5. Multiply diagonals, so we got 15 minus -14, which would be, ends up being 15 plus 14, which is 29. And that's the determinant of that matrix. It's a property of that matrix. The fact that it's not 0 is important. When you get into linear algebra, if you're going to be an engineer or something, you're going to take some version of linear algebra. So when you get into that, the determinant of that matrix not being 0 is important. It's not necessarily so amazing that the determinant is 29. It's the fact that it's not 0 that's important when you get into the linear algebra side of things. So, but very, very simple to do. You can do that with the calculator as well if you're nervous about your multiplication skills or your ability to type a subtraction problem into your calculator. You can do that with the calculator just by going to the matrix menu. Go over to edit, just like we did when we were doing our REF. Put a 2 by 2 matrix in there. 3, -2, 7, 5. And then now to get it to do the determinant, you go to the matrix menu, go over to math, and the very first option, DET parentheses, is the determinant of that. And then you just got to tell it which matrix to do the determinant of. Hit enter, and there we get 29, just like we did. Okay, so it can be done with the calculator very easily. I'm slower at typing them in than I am at working until they get like 4 by 4 or larger. I can do 3x3s are not too bad to do by hand. They're not real fun, but they're not too bad. So let's look at a 3x3. So determinant of 2, -1, 3, -2, 5, 1, 0, 6, -9. The way that you do a 3x3 by hand, there's a couple different ways to do it. One way is to break it apart into multiple 2x2 matrices and then add and subtract those in the right way to get that. Another way that only works with 3x3s is to copy the first two rows again and then do all these diagonals and then do the diagonals the other way and subtract. I'm just, I'm not expecting you to do this by hand. I don't really want you to do it by hand. It's not going to benefit you to do it by hand, honestly. So I would say just do that in the calculator. So put that 3x3 matrix in your calculator. DET, yes. Should be getting a negative number. Yeah, -120. What you should be getting. You guys are much faster at typing these in than I can be at this point. -120. Again, not so fascinating that the determinant is -120. The fact that it's not 0 is fairly important in the world of linear algebra, that it's a non-zero determinant. So any determinant that you have to do, 2x2s, I'm going to do those by hand just because they're quicker, and it takes me too long to type it in, then go through the menu to get the determinant of that. I can just do multiply, subtract. That's really easy to do. Anything bigger than a 2x2, I would do on the calculator. No ifs, ands, or buts about it. Okay, so make sure you got batteries and you got your folks that got the newer calculator. Make sure you got it charged up before you come to class and stuff, because you're going to use it to do determinants and all that. And we're going to mention this. There's this thing called Cramers Rule. Not Kramer like from Seinfeld. This is a different guy. Y'all probably don't even know who I'm talking about. Cosmo Kramer. But Cramer's Rule is another way of solving systems. Solving systems of equations using determinants. If you see the instructions tell you to solve a system by Cramer's Rule, just do it with RREF. It's so much faster to do with RREF, because with Cramer's Rule, the way it works is you've got to set up, technically, depending on how many if you're dealing with a 3-variable system that's got X, Y, and Z in it, you have 4 different matrices that you have to find the determinant of. 4 different matrices that you have to find the determinant of, and use those answers to find the solutions out of that. Well, we already have a really good way of getting the solutions with RREF on the calculator, the way you intended for you to do that. One of the other things that you kind of lose with Cramer's Rule is that infinitely many solutions scenario where you can solve for the variable of choice, whether it's Z or Y or whatever. You lose that with Cramer's Rule because you're dealing with determinants there. And what you find out with the determinants when they are 0 is that means there's no solution, but you lose the consistent and dependent case with Cramer's Rule, and you've got to go about it a different way. You end up with this 0 divided by 0 scenario, and that doesn't really work out real great with division, because we can't divide by 0. But can you divide 0 by itself? That's this whole indeterminate thing, you know, that mathematically just doesn't make sense. So if you see Cramers Rule, it says solve by Cramers Rule, or if it says solve this system of equations by any other method, you're going to use RREF the way we did yesterday or the day before. Okay, that's what I want you to grab out of that. All right. All right. Now let's look at some matrix operations. Really, really easy stuff. The matrix operations, the first one we'll talk about is scalar multiplication. It's kind of like distributive property. That's kind of like what it's similar to. So like example C, maybe you've got -2 on the outside of a matrix that's got 3, 6, 4, 8, -6, 7, -5, 3, 0. All that means you do is multiply everybody on the inside by -2. That's scalar multiplication. So -2 times 3 do -6, -12, -8, -16, +12, -14, 10, -6, and 0. So you just distribute this number to every element in the inside that matrix. That's scalar multiplication. That's another one of those things, no matter really how big it ever gets, I don't do that with the calculator just because it takes me longer to type that in than it does to just do that simple multiplication with that. Now, if that was like some weird fraction out here or something like that, maybe then I do it with the calculator just to save myself some work out of that. You can do it with the calculator. Let's look at that, how to do that with the calculator. So just so you know that it can be done. So we're going to do a matrix. Go to edit. Let's put that matrix in there, 3 by 3. Doesn't necessarily have to be a square matrix to do scalar multiplication by. You can use a scalar multiplier on any matrix, honestly. Just happen to have a 3 by 3 here. So 3, whatever. 3, 6, 4. 8, -6, 7, 8, -6, 7, -5, 3, 0. And then on the calculator, you'll just say -2 times, and then go grab that matrix. And there we have the same matrix that we got by hand. Oh, excuse me. So scalar multiplication, really an easy thing. And it doesn't matter what size the matrix is. You can do scalar multiplication no matter what size it is. Doesn't have to be square or anything like that. Next operation we'll do is addition, subtraction. They must be the same size. So you can't add, you can take a matrix that's this size 2, -6, -5, 8, draw my bracket, 10, -11. Seth, I hate to be, you got an earbud in your ear, and that's rude. All right, so if I'm going to add a matrix to one what size is this matrix? 3 by 2. So if I'm going to add or subtract a matrix from that, I'm going to have one that's the same size. So, I'd make one up that's that size. -5, -8, 13, 6, -14, and 4. Got to be the same size, and you're just going to add matching pieces. This is another one of those things. I normally don't do it in the calculator. It can be done in the calculator just by typing in this is matrix A, this is matrix B, and then telling your calculator matrix A plus matrix B out of that. But I usually don't do that if it's just a simple addition and subtraction, because you can do that without that. So 2 plus -5 is -3. -6 plus -8 is -14. That would be 8, 14, -4, and -7. We've added a matrix. Subtraction works the same way. Got to be the same size. If it's not the same size, it's just an undefined operation. Your calculator will even tell you that it's not defined. It'll give you an error and it'll say dimension mismatch is what it'll say with that. It just means the dimensions don't match, so we can't add or subtract those. What happens with this particular type of stuff is they may combine scalar multiplication with addition and subtraction. And that might be a time where the calculator might be a little bit more handy to do. They may give you like a list. You'll see in the practice, they give you a list of matrices. The best thing to do is just go ahead and type all of those matrices in at the beginning, and then you could use the calculator to generate whatever problem they give you with operations wise. They might say 2 times this matrix plus that matrix, so you just do your scalar multiplication first. Order of operations is still the same with matrices as it is with regular numbers. Multiplication comes before addition and subtraction, that sort of thing. The only thing is we don't have division with matrices. That doesn't exist. Okay. All right, so there's addition and subtraction. Let's get some multiplication. Multiplying matrices. When you're multiplying matrices, your row of the first column, or row by column, is how matrices are named. When you multiply 2 matrices, the columns from the first one must match the rows from the second one. Okay. So, for example, if we're going to multiply 2 matrices together, and let's just get an example here. Example E, I guess. Here's our matrix: -2, -2, -3, 5, -7, -8, +12, times 10, 11. Okay. So what size is this first matrix? 3 by 2. What size is the second matrix? 2 by 1. You can multiply those 2 together because those match. So when you look at multiplying, it can only be done if the numbers in the middle match, like when you look at the dimensions. Matrix multiplication is not commutative because of that. Meaning you can't swap the order and it gets you the same answer. If you swap the order on this one, you can't even do the problem, let alone get the same answer for it. Okay, so this is where some of the things with regular numbers and matrices don't match up. So 2 by 2, or 2 and 2 here on columns and rows, they match. That means you can do this, and you're going to end up with a 3 by 1 as the answer. That's coming from row by column out of that. If you're doing this by hand, you take each row times each column and then add. So it'd be 2 times 10 is 20 plus -33. And then you do 5 times 10 is 50 plus -77. And then you do -80 plus 132 to do that. That's how it happens. I'm not expecting you to do it by hand. I would put those in the calculator and let it crank out my answers out of that. So that's what we're going to do. So let's go to matrix A and put in that 3 by 2 matrix. 3 by 2, 2, -3, 5, -7, -8, 12. Okay, and then I'm going to go back to the matrix and I'm going to put in the matrix B a 2 by 1, 10, 11. And then I'm going to tell my calculator matrix A times matrix B. -13, -27, +52. A 3 by 1 as the answer. If you want to do them by hand, we can do a whole session on that. I enjoy doing them by hand. They're actually kind of fun. This is one of my favorite topics in math is linear algebra stuff. But I don't expect you to be able to do them by hand or have to do them by hand. That's just not something is something we hang our hat on in here. You go a little higher maybe, but not in here. Okay. All right. So matrix multiplication. It is not commutative. Make sure you remember that you can't change the order and get the same answer out of that. All right. One last thing is finding the inverse of a matrix. Very tedious and long task if you're going to do it by hand. It requires, depending on the matrix, tons of row operations to get it to happen. So you would, like on that quiz, you had that thing that had 3 row operations. Well, that would just barely be the beginning of getting the inverse of a matrix with that. So to find the inverse of a matrix, one thing you got to make sure of, it's a square matrix. With the determinant not equal to 0. Okay, that's kind of a prerequisite to being able to find the inverse. If you typed a matrix in there and tried to find the inverse and its determinant was 0, then it would give you an error. So it's not something you're going to have to like separately check. You're going to find that out when you try to do the inverse of that. So when you do the inverse, you're going to take a matrix. So let's call this matrix A. I don't know what letter I want. G, F. Matrix A, and let's just do a 2 by 2, 3, 1, 2, 1. Okay. A inverse, the notation is like function notation for inverse functions, just like a -1 exponent. That's the notation for the inverse. So in your calculator, this is what you want to do. Put that matrix in there. Second matrix, go to edit. This one is a 2 by 2. Works the same way for 3 by 3, 4 by 4, 5 by 5, 26 by 26. It works the same way. And just put that matrix in there. 3, 1, 2, 1. And then you're going to go to the matrix menu and grab that matrix name. So you'd put it in A. And then there's an inverse button on your calculator. It's really nice there. Right here, the same button you hit second normally to go to matrix. You're just going to hit the X inverse button. Should get a little -1 exponent happening. Then hit enter. And it'll crank out an inverse matrix. That inverts that matrix. Yes, like I said, it is possible to do by hand, but it takes tons of row operations. And I can show you how you start out, and then it's pretty tedious to do by hand. 1, -1, -2, 1, -1. I copied that. Yeah. So there's the inverse. If you're going to do this by hand, this is really what you do. I'm going to draw a line. I'm going to put identity matrix there. You know that. Remember when we do RREF, that ends up with a diagonal 1. Then you would end up doing row operations to get this 1, 0, 0, 1 on this side, which would take quite a few row operations to do. I mean, you'd have to end up being. I would probably start out with multiplying by 1/3 on row 1 to turn that into a 1. Turns that into a 1/3, but I can get rid of that in a minute. And then I would say, okay, well, -2 times row 1 plus row 2 gets a 0 right there. And you'd go through those row operations until you had this matrix on that side. Whatever ends up over here is your inverse, which would be what we found with the calculator. So doing it by hand is not a fun thing at all. We used to have to do these by hand, and they took some of them took quite a while the bigger they were to do that. There's really not a there are some ways with the 2x2s. There's little shortcuts you can take, but when you get bigger than that, the shortcuts kind of start going away because they don't always work. Because the bigger the matrix, the more complicated things happen inside of it. Okay? So it's not. You can verify that 2 matrices are inverses. Okay, and that's the last thing we want to talk about is verify inverses. And with functions, we did function composition. To verify inverses, basically all we have to do is multiply the original matrix times its inverse, and then it's going to equal the identity matrix of that size. So like with example F, we had 3, 1, 2, 1, and we found the inverse to be 1, -1, -2, 3. We found that to be the case. If I multiply those two together with matrix multiplication, I'm going to get a 2x2 back, which is right. This is the same size. 3 times 1 is 3, plus 3 times, or 1 times -2. That would be the +1 there, and then 3, -3, +3, 0 over there. And then 2, -2, 0, and then -2, 3, 1. And you get that diagonal of 1s over there. So if they ask you ever to verify that 2 matrices are inverses of each other, multiply them together. If you get that back, the diagonal 1s and 0s everywhere else, then they are inverses. I just multiplied these 2 matrices. If I were you guys, I'd do it with a calculator. I'd just multiply them together. You can, with the calculator, you can do this nice thing where you go matrix A times matrix A inverse, and that's going to get you that correct. If they're 3x3 matrices, you'll have a matrix that's 1, 0, 0, 0, 1, 0, 0, 0, 1 for 3x3. So you have what's called the I3 matrix, which is a 3x3 with just a row of 1 in each row diagonally out of that. So it's really, really just a simple multiplication to verify that. Technically, we did in function composition to verify inverses. We did it the other direction as well. Technically, true verification would be A inverse times A also gets that. It goes one direction, it's going to go the other direction. I promise. Okay. Out of that. So really a lot of calculator stuff in this. Page 878, 7 through 42, good ones. Page 893, this is the second section. 9 through 40, 67 through 70. Make sure that if it asks you to solve a system of equations, how are you going to do it? RREF. That's no matter what the instructions say. If it asks you to solve the system, you're going to use RREF to do it. There's no sense in learning the Cramers Rule because, again, you lose a little bit when it's infinitely many solutions with Cramers Rule. You don't get the nice, easy way to get the solution in the form of Z or whatever out of that. But that's 12.3 and 12.4. A lot of calculator stuff here at the beginning. Make sure you can do it because it's going to be needed when we get to the later stuff.